Okay, so here we have an electrostatic problem. I'd like to solve. We have a disk, radius r, and we put a charge q and distribute it uniformly across or like on top of the disk, okay, such that its surface charge density is a sigma coulomb per meter squared, okay? And we would like to compute the electric field some distance z, some distance z, say a point P up here, okay, above the disk. All right. So how do we go about doing this? Now we are going to leverage some of the results that we got in a previous video where we computed the electric field due to a ring of charge. So the idea here is to treat this disk as a bunch of rings and compute the electric field contribution from each ring and then add them all together. Now, from the previous from the previous example, we had a disk like this of charge q, and right above it, p. This has a radius r. Or in this case, let's just take its radius to be little r. And at point P, which is a distance z above, the electric field was, you can go check that video out, K ZQ over Z squared plus R squared to the 3/2 power. And that was vertical, strictly vertical, going straight up. You can either E sub V or you could say E sub Z, doesn't matter. So what do we do here? We basically get our disk and we break it up into rings of radius r, little r, with just a tiny thickness dr. So let me elaborate on the ring somewhere else. So this black ring here, I'm gonna look at it, maybe use a different color down here. So this is how we are going to look at that ring, okay? So here's the ring. Try my best. There you go. Again, and this is a distance r. So we're going to have a ring of a little thickness, okay? And this thickness here is dr. Obviously, this will carry charge dq, some element charge. Remember, q is plastered on the whole disk. So this is just a strip, a little ring inside that disk is going to carry some element charge, all right, some infinitesimal charge. We're going to call it dq. So now, right above, so right here above, at point P, we're going to have an electric field pointing vertically up. So the electric field for that, the element electric field, the infinitesimal electric field from this ring of charge is going to be K Z dq over Z squared plus R squared, so 2 here, to the 3/2 power, okay? Not sure why the pen's acting like this, but okay. So basically we have this right here, this expression that we got on top, except for this dq right there, I will put, I mean, for this q, I'll put a dq. And instead of the radius, so this is supposed to be a little r. It's supposed to be a little r squared. Okay. All right. Little r squared. So my job now is to integrate, to add up all the contributions from these little dqs. So let's go ahead and start setting up the problem. So now we already know the electric field, again, is going to be vertical up, vertically up. Vertical up. Okay. But what is dq? Okay. I cannot obviously integrate over dq. I have to put it in something more meaningful to integrate over, which is basically the radius. So I start with a small ring, then I make a bigger ring, then I make a bigger ring, and I keep going until I get to the edge of the disk. So I add up the contribution from these rings, and what's changing from these rings? Obviously, the charge on the ring is changing, but the radius of the ring is changing. Each of these rings have a bigger radius. So what is the charge dq? The charge dq is sigma times, this is the area charge density, area of, one ring. What is the area of one ring? Look at this ring right here. It looks like a strip. What if I cut it here and then I expand it, okay, unwrap it, if you may. This is what I'll have. I'll have a 2 pi r for the circumference, and I have a little dr for the thickness. So the area of that ring is 2 pi r, which is the length. Again, it's just a rectangle. 2 pi r is the length, and dr is the width. So dq equals sigma times 2 pi r dr. So I plug it into the electric field. dE equals the bottom z squared plus r squared to the 3/2 power. And on top, k, z, again, z is constant. dq now, we said it's sigma, which is also constant, 2 pi r dr. All right. And it looks like this is the extent of my integral, because at this point, all I want to do is start increasing the radius of the ring and start adding these contributions. So the electric field, E, K is constant outside the integral, Z is constant outside the integral, 2 pi sigma outside the integral, and that's it. The rest has to be inside the integral because they depend on R. All right. And I'm going from 0 to the radius of the ring. Right? The radius of the ring is capital R. So this is a standard integral. Okay? Where basically we use substitution. We let z squared plus r squared equals u. We'll do a u substitution. Okay? So, okay. So du is 2 r dr. Well, if you look carefully, I have the r dr over here, and I also have the 2 over here. So I can combine 2 r dr as du. So now the integral will change. Again, I'm not going to worry about the limits of integration now, because I want to go back and put everything in terms of little r. Equals kz sigma pi integral. Don't worry about the limits just yet. Let's do it first in terms of u, and then we'll plug in the limits after I plug in back to r. So 2 pi r dr, that's du, over u to the 3/2, which equals kz sigma pi integral u to the negative 3/2 du. This is just a simple power rule integral. Okay, where basically E is kz sigma pi. We add 1 to the power and we divide by the new power, right? So when we add 1 to negative 3/2, we get negative 1/2. So that will be u to the negative 1/2 over negative 1/2. Now remember, in our mind, I want to keep things in terms of r, where I go. We can actually, maybe we should change limits of integration. Shouldn't matter really. So let's change limits of integration. Will that work? Yeah, let's do it. Here, when r is 0, u is z squared, right? When r is 0, u is z squared from this right here. Here is r. Okay. So u is z squared. That's from this equation. And then when r is capital R, u is z squared plus r squared. All right, well, we can just go here from z squared to z squared plus r squared, z squared. Now you could go back and substitute u and then keep the limits in terms of r. But I want to just try it this way. Should get the same answer. All right. So now what do we have? Okay. From z, I have to make the limits from z squared to z squared plus r squared. So let me simplify this here a little bit. So I'll get here a negative. Let's keep the negative inside. So basically a 2 k z sigma pi negative 1 over the square root of u, basically. From z squared to z squared plus r squared. All right. So let's plug it in. 2 kz sigma pi. Plug in z squared plus r squared. So I have negative 1 over the square root of z squared plus r squared minus, and I have a minus in here. So got a plus 1 over the square root of z squared, 1 over z. All right. So what can I do now? I can probably do the same. So I can let this z in right here. So this will be 2 k sigma pi. This z will multiply 1 over z, will give me a 1, minus the z will multiply that one, will give me a z over the square root of z squared plus r squared. But now remember, I need to go back to q. So what is q in terms of sigma? Remember, q was the charge that's plastered over the area of the disk, and it's uniform, so q is sigma times the area of a disk. But the disk is a circle, right? Its area is pi r squared. Okay. So if I want things in terms of sigma, I stop right here. If I want things in terms of q, I just gotta take it one little step further and plug in E equals, now sigma is going to be q, so sigma pi, this sigma and pi right here will be q over r squared. So here's the 2k sigma pi q over r squared times 1 minus z over z squared plus r squared under the square root. Okay. And this is it. This is the this is the electric field from a disk, a distance z above above the disk. Okay, there it is. Again, we made use. Now, maybe what I should do is do another video where we do not start with this result right here. We don't start with this result, but instead break up the disk into little area elements, okay? And then add them all together across the radius and going in a circle. So look out for a video like this. That is more basic than this one, because this one depends on a result that was done in a previous video. If we didn't do that result, then we could not have done this. The other one, we'll just start from basic principle, basically break up, we'll create, you know, maybe elements like this. Here's the center. We'll create element charges like this. And then we integrate this going in a circle, and then we'll integrate this going up. So we'll have a double integral. But as you will see, the angular integral going around the circle will be straightforward. That one will give us, as a matter of fact, that integral will give us this 2 pi r right here. Okay. It's just the circumference of that circle. Anyways, all right. So this is it for a charged disk with a uniform charge density. All right. Hopefully this was helpful.